Namaskar. So we are starting rectangular microstrip antenna. Now in the rectangular microstrip antenna, today we are going to discuss the design. And here the design is according to the method of analysis. So there are multiple method of analysis. So we are going to discuss the transmission line model. So this is what the transmission line model method. So what is it? So that we are going to discuss. Okay. Now here in the methods, there are two methods. One is the transmission line model and another is the cavity model. Okay. So in the transmission line model and cavity model, so this transmission line model method is comparatively easier, but the cavity model method is comparatively accurate, but it is complex. The cavity model is generally the complex. So in general sense, the transmission line model is used for the design of the microstrip antenna and mainly the rectangular patch. So why rectangular patch? Because rectangular patch is the most widely used configuration. So this is the most widely used, and in general, this is what the configuration consider. So this is the method of analysis. Now we will go for the transmission line model by using the rectangular microstrip antenna. Now this is what the rectangular microstrip antenna using the transmission line model. Now in the transmission line model, what we are doing here. So in the transmission line model, here we are going to discuss the model by using, we are going to discuss the model by using transmission line model. Okay. So what is this? This is a transmission line. Okay. So although the transmission line and the microstrip antenna has the similarities, so this is what the transmission line, as you know, the transmission line, this is microstrip line. Okay. Microstrip transmission line. So this is what the upper conductor, this is what the width of the conductor, this is what your length of the conductor, and whatever the dielectric constant of these substrate, that is given by epsilon r, and this is what your height of the substrate. Okay. And thickness, this is what the thickness of the conductor. So this is what the general transmission line is there. So this is microstrip line. Okay. Now we have to understand what is this fringing effect. So we have to understand what is this fringing effect. So this fringing effect has a significant importance. Now what is happened in the transmission line, this is the electric field. This line of forces, these are the electric field, and magnetic field is in this way, that is in the around this. So in the magnetic, in this electric field, that is the electric field intensity, electric field line, this is what the upper patch and this is what the ground plane. Now these lines, it comes in the air and it goes inside, comes in the air and goes inside. Some part goes directly from the substrate. Now the problem or the thing is, here the lines are in the air. This electric line of forces, that is electric field, that is in air, and remaining that are in the substrate value is epsilon r. So here this cause a fringing effect. Means what is the fringing effect? Whatever the actual epsilon r, this epsilon r for this substrate has the particular epsilon r. So this epsilon r, whatever this substrate is having, that epsilon r will not be as it is, because this epsilon r may be greater, is actually the greater than 1, maybe greater than 2 also, but here it is in the air, and we know the epsilon for the air is epsilon 0 and it is epsilon r is 1. Okay. So some part is having the epsilon r 1 and some part is having the actual epsilon r. So this impact, whatever this entire thing will have some change in the dielectric constant. So this is called the effective dielectric constant. So as this substrate, so what the effective dielectric constant is there. So we have to see that is what is the effective dielectric constant of this substrate and how this effective dielectric constant we are going to calculate. Okay, so this we are going next. Now in the effective dielectric constant, what is the effective dielectric constant? The effective dielectric constant is the dielectric constant of the uniform dielectric material so that the line has identical electrical characteristics. Now here you can see these line of forces, it goes, this is in the air and some are in the substrate. So two different dielectric constants are there. So to avoid this or to understand this, these both dielectric constant we can take at an effective manner. So how to do that? So here generally this is what some conditions are there when we are going to develop a formulation. So there are some conditions. So here this is condition W by H. W is the width of this line and H is the height of this substrate. This is what your H, height of this substrate. So W by H ratio, this ratio is greater than 1. If this ratio is greater than 1, then we can apply this formula. So what we have done, the effective dielectric constant, it can be calculated. This epsilon R plus 1. What is epsilon R? That is, this is the dielectric constant of this material. This is epsilon R. Okay, this material, that is this substrate having the epsilon R. And this 1 is what? For the air. So it goes through the air. So the average is taken. Epsilon R plus 1 by 2 and plus epsilon R minus 1 by 2. So it is the actually epsilon R plus 1 by 2. This is what the actual. So here actual they considered that this epsilon R and this, they are considered equally. But some additional part is also considered. This is what the additional part. Epsilon R minus 1 by 2 and plus the ratio of height and width is considered 12 H by W. This is what the height, this is what the height of this substrate. Okay, this is what the height of substrate and this is what the width of this patch. Okay, so this ratio and it is under root minus 1 by 2, that is under root. Okay, so this is the formula. By this formulation we can calculate the effective dielectric constant. What is the effective dielectric constant? That we can consider this entire substrate. This entire substrate having the one dielectric constant, as this is the air having dielectric constant 1 and this epsilon R, maybe anything, it may be of the different range. But this formula is empirical, or the, you can say, the approximate formula. What is its impact? It has impact for the different frequencies. If you will use the frequency, so here this is the graph. So in this graph, whatever the different frequencies, for different frequencies, it is having the impact. That is, the frequencies is divided into the 3 parts. What is that? One is the frequency, that is this frequency can be lower frequency 9 to 13. That frequencies are there, frequency variation, and here the effective dielectric constant, that is the value of effective dielectric constant, what will be that? Now if you will take the dielectric constant, here I will start the dielectric constant. I will take epsilon R equals to 2.33. okay, so for the 2.33, it is hardly there is a change. It comes down because due to this formula if we calculate, so it comes down, and here there is a little bit change in this range, and then almost it is constant. So you can observe for the range of the dielectric constant is in the range of 2.33. So it is almost constant for the range of frequency. So this is a long range of frequencies considered. But as we will go for the higher dielectric constant, this epsilon R equals to 6.8. the actual the substrate having the dielectric constant of 6.8. If it is taken, then as it is 6.8, this is the effective dielectric constant. So the effective dielectric constant is same for the range of frequency till 10. Okay. If you go beyond this frequency, then there is an increase, and again this is the thing. So whatever this dielectric constant, effective dielectric constant, has a significant change for the higher frequency. And if you will go for the higher value of epsilon r, that is 10.2, so it has a drastic change. 10.2, so it is around 10. It is around the 10 for the higher frequency. So we can see this fringing effect is having less impact at the higher frequency, but it has a significant impact at the lower frequency. But with reference to the epsilon, that is the dielectric constant value also. If the dielectric constant is in the range of 2, it has almost a straight line. But as you will increase the dielectric constant, it has a change over the frequency. And these observations are taken for this particular antenna, where the width is taken 0.125 inch, that is 0.3175 centimeter, and height is 0.127 centimeter. So this is what the impact. So this we have to study, and this is called the fringing effect. Okay. So this is the one parameter. Now we will go for the another. So effective length, the second one is the effective length. Now this is what your patch, and this is what it has a contact, the electric field. Now electric field is over this patch. This is the black one is the actual patch. So over the black portion, it has the linking, that is the electric field of line will be there. But there will be from outside this way also, it is the electric line of forces. So this is electric field. So due to this impact, as we have the different dielectric constant, effective dielectric constant, but it also has the significant impact on the length. So this is what the patch, this is the top view. Now due to this link, whatever this line of forces are there in this particular area, in this area, this line of forces are there. So what happened due to this line of forces, due to this electric field, okay, due to this electric field extended, what it appears, the actually the antenna actual size, the patch size is extended. Actually it is this much, actually it is this much, but due to this impact, this effect, this particular effect, that is fringing effect, it appears to be extended, and this is called the delta L. There is the some length is change on the both the side. Actual length is this. So what will be the actual delta L? So this is again based on the effective epsilon effective. As just now we have calculated the epsilon effective. So this is one parameter. W, that is the width of your substrate, and this is width of the patch, and this is H, height of the substrate. So these parameters, these are the parameters that will have the impact on what, on your the entire equation. So here this is what the W by H here, sorry, delta L by H, this formula is used, and based on that, what will be this delta L is calculated by this formula. So we are taking effective epsilon r. This is generally the empirical result. Empirical means based on the multiple observations what is done. So based on that, this formulation is done. Okay. So by using the concept of the transmission line. So this is what one constant, that is 0.412 epsilon r effective plus 0.3 W by H plus 0.264, and epsilon r effective minus 0.258 into another bracket W by H plus 0.8. So this is what the formula. You need to know this formula for doing the design. Okay, so when you will have the effective length, when you will calculate the effective length, so the effective length can be calculated by adding this part. So why 2 times of delta L? Because this delta L is on this side and this side, both the side. So this is what 2 times of delta L is added. So this will be your effective length. Accordingly, you can calculate the actual length and the effective length, the effective length. So this is what the important thing for the calculation of the length. So one thing we have calculated, that is this effective dielectric constant, then L effective length, that also we have calculated. So these two things we done. Now we will go for a design procedure. Now if you want to design a particular antenna, then how we will design? Okay, so for the design, you can have, this is the design procedure. So in this 4 step, you can design a rectangular antenna. So very first is you have to calculate a W, that is the width. Okay, so where V0 is the free space velocity. So this is what the W, 1 upon 2 FR, that is the frequency of resonance. So you should know at which frequency you have to design an antenna. So this is what your frequency of resonance, under root of mu 0 epsilon 0. So these constant values are there that we are aware, into under root 2 upon epsilon r plus 1. So in the design, you have to choose a substrate. What will be the dielectric constant of that substrate? So that also you have to do. So this formula is simplified here. That is, we know that 1 upon under root mu 0 epsilon 0 is V0. And this is V0 is nothing, the free space velocity of light. That is 3 into 10 to the power 8 meter per second. This you know, you put it here, and 2 times of the resonance frequency, at which frequency you would like to design an antenna. And this you can put in under root of 2 upon epsilon plus 1. So by this you will get the width of the substrate, width of the patch of your rectangular patch antenna. This is step 1. Then second, determine the effective dielectric constant of the microstrip antenna. So just now we have discussed the effective dielectric constant, how can be calculated. So effective dielectric constant can be calculated. Okay, once W is found, here W is found, and determine the extended length, that is delta L, using the previous formula. Just now we have used this formula. This is the delta L. So by this height is given, so delta L can be calculated. Okay, and the actual length of the patch, now it can be determined. So actual length can be determined this particular formula, that is 1 upon 2 FR, that is 2 times of frequency, under root of epsilon R effective. So you can take the epsilon R effective, and this mu 0 into epsilon 0. Maybe sometimes it can be lambda by 2, but very specific it can be by this formula, because as your effective dielectric constant is the major role on the size reduction, and this is the constant. Okay, and you are subtracting actual length, so you are subtracting this 2 by delta L, because you have to fabricate the antenna, so you have to subtract it. So this is what your effective length minus 2 times delta L. Okay, so this we did. So this way design we have to do. So only 3 parameter we have to calculate. The W you have to calculate. Then dielectric constant, that is the effective dielectric constant, you have to calculate. Then you calculate delta L, and then you calculate L. Only 4 steps. Delta and L I can consider a 1. So we can have a design of the problem. So here now we will go for the designing a particular problem. We will go for a particular design. Now here I will have this as a design. So this design is design a rectangular microstrip antenna using a substrate, that is RT dieroid. Okay, so RT dieroid is one of the substrate, RT dieroid, with dielectric constant. So here the dielectric constant is given. Dielectric constant is 2.2. Okay. So RT dioide is one of the substrate having dielectric constant 2.2. H, that is the height of the substrate, is 0.1588 centimeter. Okay. So generally we are using a SI system. So we use this, we convert this centimeter into the meter. Okay. And to resonate at the frequency of 10 gigahertz. So we are asked to design it for the frequency of 10 gigahertz. So for the frequency of 10 gigahertz, you are asked to design an antenna. That is the rectangular antenna. So how to design? So very first, as we have done the design procedure, so we will go one by one. So what is in the design procedure? What is the first step? The first step, we have to find it out, the W. So this W. So W formula is 1 upon 2 FR. So you put the value of the frequency, that is 10 gigahertz. And this mu 0 epsilon 0, put the value, that is 2 epsilon R. Epsilon R is 2.2 plus 1. So this way it is simplified, that is V upon 2 times frequency of resonance. So you put the values. So what I will put, W equals to this 3 into 10 to the power 8 meter per second and 2 into 10 gigahertz. So 10 gigahertz means that is 10 into 10 to the power 9. Okay, 2 into 10 to the power 9, and this is 3 into 10 to the power 8. Okay, so here 8 and it is here 9. So you can 8 you can cancel, so it remains as 30. Okay, 10 to the power 8, I have removed 10 to the power 8, and from here 10 to the power 8 is also removed. Okay, so it will be this way. And then 2, you can put a 2, epsilon R is 2.2 plus 1. You do this calculation. If you will do this calculation, so you will get in terms of meter. So it is simplified for the understanding purpose, that is in centimeter. Please be very cautious about the unit. Use the all SI unit, SI system unit. Frequency is in hertz. So if it is gigahertz, then take it to 10 to the power 9. Then whatever the things are there, the speed of light, that is 3 into 10 to the power 8. Accordingly, you can get. So this is with the answer you will get. Now next is what? Effective, whatever the effective dielectric constant that we have to calculate. So what is the formula for effective dielectric constant? This is the formula we have for the effective dielectric constant. This, the epsilon R is with us, the epsilon R, H is with us, W, just now we are calculating W. So by using all these parameter, these 3 parameter, epsilon R, H and W, and this W by H ratio is greater than 1, you can just verify this W by H. So the W is 1.168 and H is 0.1558. So it is far more greater than 1. Okay. So your height, generally this height is very small as compared to the W. So you can verify this. So it is verified. So we can utilize this formula. So you just put the values. So I'll put the values in the formula. Epsilon R is 2.2 plus 1 upon 2. Epsilon R 2.2 minus 1 upon 2 into another bracket 1 plus 12. This height. Now this height you can, as this is the centimeter, you can put, or you can convert it in the SI system. Okay. So these values are put and take a under root. So if you will do, so the effective dielectric constant you will get 1.972. Initially it is 2.2, it reduces. So effective dielectric constant, always it will be less than the actual dielectric constant. Epsilon R is 2.2, effective dielectric constant is less than that, that is 1.9. If it is greater than that, then something is wrong in your calculation, you just verify it. Okay, so always your effective dielectric constant will be less than the what your dielectric constant. Okay, so effective dielectric constant is calculated. Now what is remain? Remain is the calculation of the L. Okay, So first we have to calculate the delta L. So delta L by H, the formula is with us. Just now we discussed this formula. So we have calculated the effective dielectric constant. W is known, H is known, effective dielectric constant is known. These three parameter you can put and rearrange it. So instead of putting H here, I have taken this H here. So this H is 0.1588 and into this multiply, and I have put the value. All the values are put. After solving this, you just do the calculation. Calculation, you must have the practice. So please have a practice for doing this calculation. Don't lose your marks by doing the wrong calculation. So please be very patient and have a practice of doing the calculation on the calculator. So this is what delta L, that is in centimeter, 0.081 centimeter. Okay, so delta L is calculated. Now what, calculate the L. So we have the formula for L. So you can have this formula or the previous formula, both are same. Okay.
Yeah.
This is the general formula, and you can have these things, just put the values in this formula. Okay, and this lambda by 2, this is what the we have the calculation for the L. Just now we have the previously that formula also you can use. So if you will put the values in the formula, you will get length, actual length equals to 0.906 centimeter. So this way your L is designed, and finally the effective length. So what will be the effective length? The length is calculated. So what will be the effective length? Effective length will be the L plus 2 times delta L. Okay. So that is will be approximately by the lambda by 2. You can verify that. Okay. And this is what you just put this value. So that will be 1.068. Okay, so this is what the final answer. And finally you just draw the figure of microstrip antenna, rectangular microstrip antenna, and mention all the parameter. Okay, mention all the parameter, and you will have this particular uh, calculation done. So this is what the design of the microstrip antenna by using the transmission line.